Hey Chem students, so today we're going to do our last lab on the battery, where we're going to take the knowledge from last lab where we did the different metal combinations to see which two different combinations of metal from the activity series were the best. And we had the top of the activity series combined with the bottom of the activity series being the best two types of metals to use inside of a battery, which if we had access to all of those metals would have been lithium on the top and gold on the bottom, but those are expensive and dangerous, so we don't have access to all that. What we're going to do today is we're actually going to just take copper and zinc. I know it's not the best of the batteries, but it's reliable and it's cheap. So we're going to take copper and zinc today, and we're going to do what we call a pile. So instead of just having one metal next to another, where in the last lab we did the copper and the zinc side by side and we connected the salt bridge, we're going to do something a little different. We're going to take the copper and the zinc, and we're going to soak some cardboard in copper 2 sulfate. And this copper sulfate will be, let me just go ahead and start doing that for you guys. So this, let's just take it off. So this copper sulfate will actually act like the salt bridge. So we're going to soak the cardboard. Instead of like the last lab, we had the filter paper that was joining the two metals together. This is going to act like our salt bridge. So the ions from the copper sulfate will be soaked in the cardboard, and it will create the salt bridge portion. So we're going to take copper and zinc, and we're just going to layer them. So it'll be the copper and then the cardboard soaked copper sulfate, and then the zinc. And we'll just keep repeating, and each layer of the two different metals with the salt bridge copper sulfate cardboard will act like one little mini battery. So we call this a pile when we stack more than one of these repetitive. You'll see what I mean. So let's go ahead and get started. I'm going to go ahead and go through the background with you guys. Also, one thing that I want you to walk away from this, because it's the end, it's the culminating lab, is that you now are going to take your knowledge of the plastic project with the polymer knowledge of chemistry and how plastics are made and recycled, and then how you can actually create your own toys or objects with 3D printing. And we're going to hybridize that in the battery project from today, where we're going to create a pile that can fit inside of a 3D printed small toy or object. And then we want that power from the electric power from the battery that we create today to actually light something up, like maybe some LED lights that we could put as like eyeballs or something inside of a 3D printed toy. And so in this final project, it would be up to the student to create whatever they wanted in the 3D print, and then just make sure that there is a hollow cylinder that they can stack their Voltaic pile from today inside, and then connect it to some LED lights or something, whatever you guys want to do. That would be the final culminating project. So I will show you an example of that at the end of this, but this is the last, so we are tying all of that together. So let's go ahead and read the pre-lab for this Voltaic pile part. All right, students, so again, you're going to have this document in your Google class. Anything that is in red here and here on the first page and over here are things I expect you to write down in your notebook or copy, and then I want you to answer or put the data in your notebook, and then take a photo when we're done and send them to me. So you guys can read this a lot more clearly in the document, but I'm going to go ahead and read it for you. So the title of this lab is called Building a Voltaic Pile or Battery Lab. The background is that we're really recreating a Voltaic pile, and that was invented in 1800s by Alessandro Volta, which is the scientist that we named the voltage unit off of, is Alessandro Volta. So in 1800, Alessandro Volta constructed a voltaic pile by stacking pairs of zinc and copper plates, like we're going to use the same metals today. Each pair separated each pair separated by cloth or cardboard that had been soaked in a solution of salt or sulfuric acid. And that's that cardboard soaking that I just told you guys about, the copper sulfate we're using. Since concentrated sulfuric acid is corrosive and dangerous, you will use a more benign electrolyte, copper 2 sulfate, in this investigation. Our purpose is to increase the voltage of the pile or battery up to 6.6 volts, which is a decent amount of voltage, so that we can actually create some electric power to, you know, light some lights or something. Our hypothesis is if I stack two metal combinations of an electrolyte soaked cardboard, with an electrolyte soaked cardboard, then I should be able to increase my voltage up to 6.6 volts because I am joining more than one battery together. So every single, here's an image of the stacking part, right? Every single copper, cardboard, soaked electrolyte, and then zinc is considered one pile of a battery, okay? And so you have to keep going to get multiple piles in order to increase the voltage. So we are going to use the cardboard. The filter paper is not as efficient. It doesn't work as well in this. And we're just going to keep repeating the sequence. Copper, electrolyte, copper sulfate, cardboard, zinc. Then keep going, just like we see here. The first thing we're going to do is just record the voltage of one little pile of copper, cardboard, electrolyte, and then zinc, and see how much volts we get with just one. And then we're going to keep going until we get... our goal is to get 6.6 volts, because that's a decent amount of power or voltage, for our function of lighting an LED lights. So we're going to record how much volts we get with 1, 2, 3, 4, 5, 6, 7. Possibly whenever we get to 6.6, we can stop. And then we want to write down what was the successful number of piles that achieved that 6.6 volts. And, you know, it might not have been exactly 6.6 volts, so how much did you get? And then here's the section I was talking about where I'll show you a video of putting it all together with a plastic project and then a 3D printed object that has a voltaic pile inside that can light some lights, such as eyes or something. And then when you're finished, you're going to just, you know, do your clever conclusion and D to G reasoning, take photos, send it back to me. All right, so let's get started. All right, one thing we're going to do to just make sure we get the best contact from the metal is to just scrape off any sort of oxidation layers we have on the metal before we connect them. So we're removing any sort of oxidized coating that has formed, because you know that copper oxidizes into the copper ion and then grabs the oxygen out of the air and forms that copper oxide, which usually is that greenish pretty look that you get on the copper buildings and stuff. This is pretty sealed up, so it didn't really have too much, but we're just going to go ahead and rub it off just in case to make sure. And then we're going to do the same for the zinc, and that will allow the best contact. I'm going to pause here. You don't need to see all the sanding. Okay, so here we go. We're going to try our first pile. So it's going to be, I have the voltmeter up here so you guys can see it, and I'm going to put the red lead from the voltmeter on bottom so that you can see the voltage that we produce. I'm just putting the copper metal on top of the voltmeter. And then you're supposed to do copper, electrolyte, and then zinc. And you want to sort of dab off that cardboard, because if it's too wet, it just drips down and it creates a short circuit. So I'm just sort of dabbing, dab, dab, dab on the paper. Okay, so copper sulfate, and then zinc on top. That's one pile, and we'll see what we get from that. So it looks like we're getting 0.8 volts. 0.8 0.8. I'm just going to put 0.8. So write that down, guys. So for the first question, it's 0.8 volts for the first question 5. Now we're going to keep going. So I'm just writing this down in the notebook, 0.8 volts. Now we're going to keep going. And after the copper, electrolyte, copper, zinc, it's one more thing of copper. We're on the second pile now. So you can see I'm now doing copper. Another. So one copper, cardboard, zinc pile is like one battery, right? And that was 0.8. So now we're saying, well, what if we were to put more than one battery stack together? Come on. So we're now working on the second layers. And then I'm going to touch this. How much? We're getting so hold on, 1.2. So it's about 1.2 when I do it just right. So I'm going to write down 1.2 volts for the second pile. Keep going. Copper. Cardboard. Let's try to pull these out. Zinc. Then how much power are we getting from that? 1.4 was like the highest I saw. I'm going to try to make them all in a nice like pile too, because sometimes just shifting and all of that makes it mess up. So 1.6 when I was able to move it around. 1.6. 3 piles, 1.6. And I'll show you my data when I'm done. I'm just trying to get this done quick. Copper. Electrolyte. Zinc. And I'm getting... Ah, shoot. What a mess. Okay, let's start over here. Copper, electrolyte, zinc, copper, electrolyte, zinc, that's the second one, copper, electrolyte, zinc, copper, electrolyte, zinc. All right, that's the 1, 2, 3, 4. So let's see. It's a lot easier to do these labs when you have your friends holding things. Me trying to do it by myself is... So we've got 1, 2, 3, 4 piles. And I'm going to try to see what my voltage is on that without it sliding around any. Alright, what do we got here? We've got like 2.12. I'm going to put 2.12. 4 piles, 2.12, and I'm going to keep going. So I'm on zinc, copper, electrolytes. Hold on, let me get some of these things out. Electrolyte, zinc. So now we're on pile 5. How much do we have now? Okay, come on. You couldn't have decreased. Alright, I have to stack it more. Hold on. Alright, so I stacked it nice and neat. You have to stack these nice, boy. It's really hard. So this is 3 volts from the 5th pile. Alright, I'm on the 6th pile, and I stacked it nice and neat, and it's 5.44 volts. So 5.44 volts for 6. Alright, we're on 7, and it's 5.89. Alright guys, so I just realized I was reading the numbers backwards because this camera is flipping the image, so it's actually the 2s. And so what that means, of course it's not allowed if we don't have some errors, is that the cardboard was soaked too long and that the copper sulfate was creating short circuits. So I redid the cardboard and I put it in just for a little bit, and then I pulled it out to dry. So hopefully we won't have as much short circuiting going on. So let's try this one more time, please. Hope it works. Okay, so I'm gonna try to do it quick. And I'm not even gonna stop to write down the numbers. You guys can do that. So copper, cardboard, which I'm gonna sort of dampen off because I think that was the problem. It's just got too much liquid and it's creating a short circuit like we said in the pre-lab. Zinc. Now that number was like 0.8 the first time. I'm just going to leave that. That's totally fine, acceptable. Still 0.8, good. Copper. Dab off that copper sulfate to dry it off a little bit. Cardboard, zinc. 1.58. I'm just going to leave the 1.2, 1.4, so 1.5. Let me read it the other way. 1.5, 1.6. That's actually what we should get. So we should have it doubling. So that's 1.6 for the second one. Copper. Dampen off these cardboards. Zinc. And so that is 2.3, 2.4, 2.5. So 3 is 2.5 volts. So you can see that the short circuiting is really a big deal. So make sure that you are dampening that cardboard so it doesn't squish out, leak everywhere. So copper, dry off the cardboard. Zinc. So the fourth pile, what do we get? 2.89. $2.8, 2.85 for 4. Copper, dry off this cardboard. Zinc. $3.3, 3.345. Copper. Dampen off this cardboard. Zinc. $3.846. Try to make this a little better here. Copper, cardboard, dried off, and zinc. Okay, so for 7, we're going down, which means we're getting some short circuiting going on. All right, hold on. Let me try to stack this better. All right, guys, so I started getting more short circuiting. So what I did this time was I cut the size up of the cardboard because I think the cardboard's just too big and dripping everywhere. So let's see if we can get it working with this one. Round 3. Wouldn't be a lab without our problems. Okay, so one more time. Copper, small cardboard, zinc. .97. Copper, cardboard, zinc, 1.8. Copper, cardboard, zinc, 1.8 something. Keep going. Copper, cardboard, zinc. We're now on 1, 2, 3, 4. 2.3. So 3. We're getting like 3 with 4 pile. Copper, cardboard, zinc. Ah, this thing is just so much fun. Ugh, no, no. Okay, guys, I'm gonna change it to 3 volts. How many can you get with 3 volts? Because without help, doing labs is just not super duper. I need more than one hand to do this correctly. Some holding. Okay, so we're gonna wrap that up. We're gonna change it to how many piles does it take to get 3 volts. And we can talk about that in our error, how we need more hands to make this work. So I'm gonna switch this to 3 for this year. Because I only have me doing this, and I got up to my highest. I'm gonna flip this around so you guys can see my data here. All right, so my highest, let's just go ahead and do this. We're gonna do 3 volts only. Sad face. Our error was we had only one person trying to pile, and I need multiple hands. So 0.8 was the first, 1.6 was the second, 2.5 was the third, 2.85 was the fourth, 3.3 was the fifth, 6 was 3.8. We almost got up to 4. What we want to do is, you should be seeing it increase by a factor of 0.8 every single time. Now, if there's like liquid dripping or I lose it, so what happened to me was that right around here, I just couldn't hold it. It was just sliding everywhere. And so then it was just not contacting well. So if I hold it, usually when you do this in the lab, like one person holds the pile all nice and tight and another person comes in with the electrodes, and then it works pretty decent. So I'm going to go with that. Our 6 let's see, number of piles to create 3 was 6, and it was a total of 3.8 volts. So, all right, I did the pile. I got the voltage up to 3.8, and now the next part is that you're supposed to do a plastic, have a hole in it, and put that pile inside there to light the lights. Of course, I'm not, you know, at school, and I don't have access to my 3D printers right now. So what I'm going to do is show you a video of a student last year doing it, and you'll be able to see what it all looks like when you actually have the 3D plastic print plus the pile inside, and then it lights the LED light. So I'm going to just show you a nice video from last year so that you see that last part. And then just go ahead and do a clever conclusion. Obviously, error, need more than one person. Short circuiting was huge. I think cutting the cardboard down to size was helping, but then the piling creates like sliding, and it's really difficult at that point with one person to hold it and then also stick these probes in, and so it just would have been nice to have a helper, but you know. All right, guys, I miss you. I hope you guys are all doing well. And that's it. Take care. I'll definitely see you guys next year for sure. So, all right. See ya.
I started the alternative energy pathway my sophomore year when I took physics of alternative energy. I learned how to build and conduct research and design in regards to windmills, solar thermal hot water systems, and solar photovoltaics. As a junior, I am taking chemistry of alternative energy, where I am learning that matter has different chemical and physical properties that can be used to generate electricity. Some examples are thermoelectric and piezoelectric energy generations, batteries, hydrogen fuel cells, metal and air fuel cells, biodiesels, ethanol, and nuclear power. Through this pathway, I have learned leadership and collaboration skills in a workforce environment that will help me with my future no matter which pathway I choose. Going on all field trips, leadership competitions, and hearing from STEM-aligned industry has helped me to become aware of all the options that are open to me in my future.